Roche State Park. My name is Rick Bruce. I'm a conservation educator. I teach outdoor education and environmental science to the various groups that come through this park. Tonight, the topic for this evening's presentation is Champlain Valley weather climber. Our guest, we were very fortunate to have as our guest speaker, Mr. Gib Brown. Gib is the meteorologist of WPTZ-TV Channel 5 in Plattsburgh. Gib holds a Bachelor of Science degree and a Master of Science degree in Earth Science from the State University of New York at Plattsburgh. He's taught in the public school systems of Peru Central School and Osceola Valley Central School for 18 years, where he currently teaches Earth Science and Physics grades 9 through 12. Mr. Brown has worked as a meteorologist for WPTZ-TV for 10 years and is the recipient of an American Meteorological Society Broadcaster Seal of Approval. And this is a very prestigious award, as it is, he's the only full-time educator in the United States to receive one. At this time, Mr. Brown.
And all that, and I still can't get the weather right. Hi. I want to kind of run this as informally as I can. It's a nice, warm, and humid night, and I'm going to learn, hopefully, some things about the North Country weather from you that might be able to help me forecast weather here a lot better. I'm from Brooklyn, New York, and looking out to see the weather in Brooklyn is like, well, you know how it is, tenements and skies, so beautiful skies here kind of help that a lot. We do have mountains in the way, we have sheltered valleys, and there's a lot of places around the North Country where we never, ever hear about, and they may be almost a different world in terms of snow in the wintertime. And very often we'll be reporting partly cloudy skies in Plattsburgh, Chazy Lake. We'll get a call from the Pump House Road up there, and somebody will say, well, we got about 8 inches of snow and it's still coming down hard. So I'm going to encourage all of you to ask questions. I'm going to try to help some of you become weather observers so that you can help us all do a little bit better job in weather forecasting for this area, because we are not a very populated area. Burlington is our main weather office here. That's where we get most of our data from. They are servicing an area just north of Boston, all the way up towards Sherbrooke, including our immediate area, and going perhaps as far south as Glens Falls. It's an enormous area when you consider that Messina, Malone, Saranac Lake, all in the Champlain Valley are also in the forecasting area. They're also closing some weather service offices within the next year, among them Syracuse, which is a major one. And so we're going to sort of be out in the woods, so to speak, in the next couple of years as these closings take place. So hopefully we can all kind of contribute to a little bit better understanding of the weather here. And maybe on a Friday night, if I'm forecasting, you know, that we're going to see partly cloudy skies and you got freezing rain up in Chazy, or it's snowing out in Beekmantown, you can kindly call us up and say, hey, look, you got it wrong, because we need to know that. So if you have any questions at any time tonight, please feel free to ask them. Very happy to see some kids among us, and that's great too, because I've got some special projects for you guys to go through. Okay? Hope you didn't have lunch or supper already. Okay, one of the things that I like to start out with is an historic approach to weather in this particular area, because it's kind of neat. You've heard of sayings around here. That the most prevalent one is, if you don't like the weather around here, wait 20 minutes, right? Isn't that the one that usually is most often heard? Okay. And it's very, very true. We have such a diverse geography. We have an enormous 106-mile long lake. We have the Green Mountains in Vermont. I guess you had a geologist last week explaining some of the various topographies around here. You have the Adirondacks to our south and to our west, the St. Lawrence Valley to our north. And we live at a very critical point on the Earth's surface. We're just about exactly halfway between the North Pole and the equator. Matter of fact, somebody very nicely painted a line across the highway in Vermont, just a few miles north of St. Albans. And it's the midpoint between the North Pole and the equator, which means that we are influenced, depending on the time of year, by air masses that come from the northern Arctic regions, as well as those air masses that come from maybe 300 or 400 miles south of Florida. They both influence our weather. So one of the reasons why weather is so difficult to forecast here is that we have such diverse weather patterns. We have storms that come from the south as well as from the north, and we have such tremendous differences in geography. It's very often found that it may be snowing 15, 20 inches. As a matter of fact, last winter, Burlington had 17 inches of snow. Plattsburgh had a dusting. Okay? Very common to see that. Very common, as we mentioned before, Chazy Lake in the Adirondacks and many community areas may receive 20, 25 inches of snow, and this area may not receive anything at all. Okay? So it's because of geography, because of uplift, because of the diverse patterns that are coming together over our region during most of the year that we have so many of these tremendous changes. We also have these long-term global things. You are looking right now at something that everybody's calling the greenhouse effect. Okay? The greenhouse effect, we're warming up. Are we? Maybe. All right? I don't know that the jury is still firm on that one. We are looking at some possibilities of warming. But did you know in 1816, the North Country was almost rendered a ghost community? We had in 1816, at this time of year, snow and ice on window panes. We had Lake Placid reduced to a town of only 10 families. We had carpenters working an entire week for a bushel of wheat. And that tremendous change in climate, unheard of in the annals of history, one that a former president designated as the year without a summer, 1816, or 1816 and froze to death, they call it. That particular weather phenomenon that year was produced by a volcano. A volcano in the Pacific Ocean called Tambora, which in 1815 blew up 7 cubic miles of rock, pulverized it into ash, put it into the Earth's atmosphere, and reduced sunlight by about 10%. Okay? So we are looking at local weather patterns, we're looking at large-scale air masses, and we also have to consider these environmental things, both human, the greenhouse effect, and natural, volcanic eruption, which also play a very significant part in our weather. And of course, weather has been something that the communities here have been very, very interested in because it meant their survival, especially 100 and 150 years ago. And a lot of things have been written down, little rhymes and riddles have come about, little parables such as, we've heard some of them, red sky in morning. Okay. The ring around the moon means rain.
Right.
The ring, and the larger the ring, the sooner the rain. You probably heard some. Have anybody heard other ones?
Dew on the grass.
Dew upon the morning grass, rain will never come to pass. Anybody else? What happens when the cows lie down? It's going to rain, right? What about some other things?
Birds on the telephone line.
Very good. Very good. Birds on the wire. Birds have a difficulty in flying when the air pressure is low. And it just so happens that when the air pressure is low, the weather's lousy. So birds aren't so dumb. They'll sit on the wire. They won't fly when the weather is going to change, especially if it's going to become inclement. Give me some other ones.
Dry grass, thunderstorm.
Okay, dry grass. Sometimes that works very well. What else?
The leaves start on the living trees.
Okay, the leaves. What else? Very good.
When chickens go in, it's a shower. When they stay out, it's an all-day rain.
Okay, all right. Now you got it. Okay. Now, we very often, and if you look at the Farmer's Almanac and you listen to Aunt Tilly complain about the bunions and rheumatism and all those little aches and pains that you get, we used to laugh at those things and say, well, yeah, right, But there are very, very substantial amounts of information we can get from that. For example, if you have rheumatism or bunions or corns or any of those maladies, they are very good indicators of lousy weather. Low pressure, lousy weather, Tissues tend to swell, impinging on nerves, and there's migraine headaches. A lot of these maladies, again, are related to weather, and they can be good foretellers of the weather situation that's coming in. Some other ones, anybody?
Is the ring around the sun the same indication of storm? I mean, you can't look directly at the sun, but if it's obscured by a cloud, a thin layer, you can see a ring around it.
Very often, yes, very often. The rings are produced by high ice crystal clouds. You get that rainbow effect sometimes. And that usually means that warm air is riding in, and it usually comes in from high altitude to low. It kind of rides over the back of cold air, which may be in your area at that particular time. And that's what produces the ice crystals. Okay, so yes.
White sunset is cold, pink sunset, or red sunset hot.
Very often, a lot of that's due to dry conditions too. Some of those red sunsets are more commonly produced by dust. Okay, and if it's been dry and warm, you get a lot of dust blowing around, and you get those beautiful sunsets. After the Tambora volcanic explosion, sunsets were viewed around the world as just totally spectacular because there's so much dust in the atmosphere. It was always a red sunset, even on the clearest of nights with the dust in the atmosphere.
I notice when the moon is further south, it gets warmer and warmer. As it comes further north, it gets cooler. You can see where it's... Oh yes, boy, I know. The moon shines right in on my bed if it's warm. But if it's cold, it'll be way back up and it won't even shine in.
Okay. I have to look at that one. Other things, combing the hair, okay? Right? Why is it that, sometimes you look at yourself in the mirror, you comb your hair, and you say, oh my God. Well, because hair is hydrophilic. It absorbs water. Okay, it actually is longer. And so if you lose your perm, well, the probability is it's going to be very humid. And it is very humid because your hair actually gets longer. Okay, drier conditions, your hair is behaving more naturally. Well, any others?
If you have a yellow sunset, does that necessarily have anything to do with pollution?
Yeah, big time. I just came back from Denver, and I saw 3 gorgeous yellow sunsets. Matter of fact, flying into Denver and flying into a lot of those areas out west, it's like looking at a bathtub ring. You get to maybe from, I'd say maybe 10,000 feet flying down to about 5,000 feet. You can actually see the layer. It just kind of sits.
As a pollution?
Yes. And I've heard the same thing for Los Angeles, too. But, yes. Man has really, really altered the Earth's atmosphere. Whether or not we can actually correct it, if we can even understand it, that's something that future generations want to see. Another one, you hear those things outside right now, those crickets. Can they tell us anything about the weather?
It's going to get hot.
Yes, exactly. Anybody know how a cricket works? or how to do it? The trick is you take the number of chirps a cricket chirps in 15 seconds and add 37 to that number, and you've got the temperature. Pretty close. And the reason that works is because crickets are cold-blooded creatures, and their metabolism is driven by the temperature outside. And of course, it's higher when it's warm. It's like the flies in your window in the fall. They're just like B-52s. They can't get off the ground. They just don't have enough energy to move very fast. Well, the crickets are the same way, and their chirping is very, very related to the temperature, and they'll chirp really quickly. I did that. My wife, my poor wife. I went out with my stopwatch a couple of years ago when I was, as a matter of fact, when I was living up in Morrisonville, just to check it out, and this cricket was chirping like crazy, and found out that the temperature where I figured out was about 87 degrees. Well, this is about 6 o'clock at night, and you darn well it wasn't that temperature. Well, what I did was I put my thermometer right next to the rock where the cricket was, and sure enough, it was 84 degrees, which was pretty close, So, okay, of course, now, yeah.
What is that criteria? What does it count?
Okay, take the number of chirps in 15 seconds, and then add 37 to it. Now, we got to watch. Of course, you got to have a reliable cricket too. You can't stop midstream or else. Okay, nowadays, of course, we use a little bit more sophisticated equipment. But the thing is that the parables have kind of given us clues as to what to look for. Because what we want to do is gather data so that we can make an accurate prediction. And it's very difficult because of the fact that weather changes so rapidly and data is so scarce, and it still is scarce. We don't do a good job on a long-term basis for weather. It's not that we don't quite understand it, it's just that we just can't collect it as it's happening. Okay? We use a lot more sophisticated equipment right now. I've got a couple right here. This is the famous weather rock. You've probably seen these before. And it's red, of course, raining. And these are our forecast goes. Here's an interesting one. This is the Davis Hill weather stick. Okay, when this is pointing up, it's somewhat fair. When it's pointing straight up, it's very fair. And when it's pointing down, it's going to rain. So, well, anyway. No, nowadays we have literally thousands of different weather collecting data from centers from around the world, and we collect a lot of information every hour, and we try to put those into forecasts. We make maps, we study the upper air, the bottom air, and we do a pretty good job. Probably we are about 87% right on a 24-hour basis. We are about 75% right on a 2-day basis, and we are about 60% right over 3 days. I don't even want to talk about the 5-day forecast because it's about gambling on 50%. Again, it's a very complex thing that changes all the time, and subtle changes can make dramatic differences in other parts of the atmosphere. Today I want to just get into some of the storms, and talking about that as a particular type of weather. We know what sunshine is, and we know what our snowstorms are like, but today I want to just talk about some of the different kinds of storms that we've had this summer here in the North Country. As you know, in the early part of summer, we had some exciting weather around here, didn't we? We had millions of dollars in losses in Vermont and floods. We had a couple of scares along the Sable River and a couple of rivers out around Saranac Lake. We had 4 inches of rainfall on Shazy when Plattsburgh didn't get anything. Flooded some roads up there, did some damage up their foundations. Not a great deal of damage, but still quite a surprise. We had reports of several quote-unquote tornadoes. Saranac had one up along Pickett's Corners. They had one up on Mark's Sawmill down there on the Irish Settlement Road. And there have been several in Vermont as well. We'll get into some of these phenomena today. I want to show you some slides and pictures of them, and then we'll get into how they form and what they are. First of all, thunderstorms, that kind of a storm system, is a summertime only phenomenon. Why? Well, it's because of energy. And energy is what drives these systems, storm systems. The energy comes predominantly from the sun. Okay, matter of fact, 99% of all the systems on Earth get their energy from the sun, including you and I. I mean, we're all solar powered in a way. And of course, the atmosphere is too. You heat a little pocket of air, and it rises. Okay, when air rises, it expands. And just like if you let air out of a tire, what does that air feel like when you let it out of a tire? It cools down because it expands. Okay? When you pump a bicycle tire up, you feel the compression part of the bicycle pump down at the bottom. It gets hot because you're forcing those air molecules together, and it heats up. You let them out and expand, it just does the opposite. It cools down. So taking a parcel of air, putting sunlight on it, maybe over a plowed field or over the Pyramid Mall shopping center, dark objects pick up more energy, absorb more energy from the sun than light objects. They tend to heat up more. You create a bubble of air that rises. As that bubble of air rises, it's evaporated moisture at the surface, and now you have a warm, moist bubble of air shooting up into the Earth's atmosphere. Well, what do you think happens to that warm, moist bubble of air as it starts to expand. What do you start to make? You start to make clouds. You condense the water. You start to condense the water, and you bring that bubble up a little further. You get those cloud droplets bumping into one another. And what do you think cloud droplets do when they bump together? Yeah, start to make rain, and then the rain falls. And now, of course, if we ever evaporate, you know what happens? You put water on you. What does it feel like when you splashes up with water? It feels good, doesn't it? Cools you off, right? Evaporation cools you off. Okay? What's the opposite of evaporation? That word is condensation. You condense. So if evaporation cools you, what does condensation do? It heats you up. Right? Okay. Well, what we have going on in clouds is we have all this air, and it rises, and it cools, and it makes rain, and the rain comes down. And the rain comes down through places where, falls below the cloud. And what do you think some of that rain does when it falls below the cloud? Before it even gets to the ground sometimes. It evaporates. And what's evaporation? It's a cooling process. And what does cooling do to the air? It makes it sink. Okay? So in clouds, we got uplifting and downlifting or downwelling, whatever you want to call it. You get this up and down and up and down and up and down inside a cloud. It gets very, very turbulent. If you've ever been in a plane, especially a small one, and you've flown through one of those things, you go up and you go down and you go up. And it's all produced because of the currents. Most of those currents are produced because of the differences in temperatures within a cloud. Okay? Well, if you get a big cloud, and you get a lot of rubbing up and down with these currents back and forth, you make something that's really, really scary. Anybody know what that is? Yeah, Meg? Good. How many people have ever gone into the library? Now, you don't have to admit this. You kind of, you got your friend over there. He's sitting very quietly reading a book, and the librarian's over there, and you take your feet, you slide your feet along the ground, and you take your finger and get real close to his ear, and zap, right? Static electricity. Okay? That is exactly what lightning is. It is static electricity. And it's produced as up and down currents in a cloud rub up against one another, and these little things we call electrons kind of accumulate at one point. And that means that, well, if you're accumulating those little things up here, you haven't got as many down here, and that produces something that we call potential, and they make a jump. Okay? And that is exactly what that is. Let me see if I can give you a better demonstration of that. Here is a little a lightning generator, and come on up here. All I want you to do, it's not going to kill you. What would you do? Let's let everyone see it now. We want everybody to see you jump. Just take your hand and go real slow down there. It's amazing that to get that jump, you want to try it? Come on up here. You sure? You want to try it? Come on up here. She's still standing, right? She just got hit by lightning. She did. Right there, lightning, look. That's lightning. That's exactly what it is. Now, if you figure that it takes a lot of energy for those electrons to make that jump, okay? Anybody have any idea how much energy it takes?
100,000 volts.
To jump an inch, it's about 20,000 volts. Now, let's go back over here, and let's see. This cloud toplet may be something like 30,000 feet from here to here. If it's 20,000 volts an inch, Can you imagine what it would take to make that jump? Probably millions of volts, huh? You don't want to stand under those, because that will cause you to blink a few times, because getting hit by that can do some pretty serious damage, like kill you. Lightning is one of the most severe one of the most leading causes of death in the United States. Now, how many of you kids play sports for a town or somebody? You know, what are the umpire's rules? If there's
They stop the game, it stops raining, or they hear lightning.
If they hear lightning, hear thunder or see lightning, the game is canceled. Why? Because so many times that lightning, this is pretty dramatic, this picture right here, but lightning isn't often this dramatic, but it is very often killer. Lightning very often will precede the storm by many, many miles. It just depends on where those electrical charges are. Very often kids will be out there in center field. Hasn't started raining. The storm is there, they can see it, but referees or umpires are saying, it's not raining yet, let's not call it. Bang, it's all over. Kid's out in center field, he's cooked. And again, lightning is that kind of phenomenon. Okay? Very often lightning will trail a storm. The storm will be gone. 5 minutes later, this blast comes out from nowhere and hits something. Just last weekend, remember that storm that went through Sunday? Okay, remember that power failure? Did anybody go through that power failure when the lights went on? Lights went off? Cable TV went off for a little while? That was about 10 minutes after the storm ended. Just that last bolt of lightning. Bang. Okay? Lightning is an extremely deadly force. Let me show you an example. Can I have those lights, please? This is a kind of an interesting thing right here. Fire department gave me that from Upper J, New York. Okay? And what that is the root of a tree that was hit by lightning. That is basically nothing more than glass. And what you see around the outside of it is the sand in which the tree root grew. Okay? And it's all fused together. And I don't know what it took to hit that thing, but I know the J Fire Department has the rest of the trunk that was under the ground. And it's an amazing thing. It was molten glass, molten sand. Okay? Now, what are some of the things that you can do to enhance your chances of coming out of a lightning storm safely? What don't you ever want to do? Stand under a tree. If it's the only tree around. If you're having to make a choice of going out into the field or going into the woods, by all means, go into the woods. Okay? Trees in the woods, there's so many of them that the chance of one particular tree getting hit is probably not that great. Okay? But if you're outside on the field, you may be the only little positively charged thing out there, and you can get zapped pretty quickly. If you ever are on a field and you feel like somebody, and if the storm brewing, and you feel like somebody's running your fingers through your hair, anybody ever experienced that? It's a kind of an imminent thing that you're going to be hit by lightning. Okay? Anybody ever seen St. Elmo's fire? Okay? Pilots, maybe, if you're out on a sail, sometimes you can see that. Well, sometimes you get that in a lightning storm too. And what happens is that lightning sets up these, what they call ionized channels. In other words, lightning kind of charges the air before it strikes. Okay? And these channels, as you can see, they're very clear here, are like greasier areas in the air for the lightning to travel through. Okay? And if you are standing like down here a moment before this lightning bolt strikes, you may feel that somebody is running their fingers through your hair. That's not it. It's that you're setting up a charge. And the only thing that we really can do at that point is to go down on your elbows and knees. Don't lie down. Go down on your elbows and knees and hope that you're not going to get hit. I've known 3 or 4 people that have actually felt that. The hair along the side of their ears just kind of went crinkly. They just felt this funny sensation. They were very, very lucky that lightning struck nearby. A transformer, a barn in one case. But if you are out on the field and you feel that, the only thing you can do is get on your elbows and knees. Now, why not flat? Well, because if you're lying flat on the ground, lightning hits near you, you're going to have enough surface area on the ground to pick up a lot of that charge, and you'll probably get pretty good electrocution. Okay? On your elbows and knees, you want to minimize the surface area that's in contact with the ground. So if lightning does get near you, you'll get burned, but you may not get killed. Okay? If lightning hits you, most of the time, you're just a statistic. Okay? There are some very fortunate people. There's a report somewhere that a guy's been hit something like 7 times. I don't know. Of course, Lee Trevino was hit by lightning. He had his 9-iron or something up one day practicing for the Masters, and he got knocked right out. And I guess his hands were blistered and everything else, but he was wearing gloves, and there was a rubber handle on the club itself. So I guess that's what saved him. Otherwise, Lee Trevino would be a statistic. Okay? Lightning is something never to fool around with. Never near water. Get out of the water. Get off the phone. Okay? A good friend of mine, Bert Redan, had his house hit by lightning, and the breakers on the house, which are supposed to shut off, didn't shut off. And apparently, according to Bird, the lightning charged through the wires, and they had an enormous amount of trouble. I mean, they had to basically rewire the entire house at a tremendous expense, because the fact that lightning can travel through all kinds of things, especially with wires. If you're on the phone and lightning hits the pole, half a mile away, you can still get zapped. Maybe not killed, but you get jolted. Again, taking a shower, lightning will travel through the pipes, maybe get you. So again, most of the things not do is a real lightning storm. Fortunately, for our area, although we do have lightning storms, we have nothing of the intensity they have out in the Midwest, where this was taken. We don't have the combination of extremely cold air and extremely moist air that we do, say, out in the Central Plains. The mountains also help us out by breaking up some of these airflow patterns and help cause a minimal thunderstorm risk here. But they are still a very, very strong possibility. The next thing that happens in storms of this nature, as what happened in Vermont, is, of course, the danger of flooding. Now here, because of some of our narrow valleys, we do sustain damage to the flooding. Yes?
Why don't you see lightning in the wintertime when it's snowing there? You usually see it.
You can sometimes see lightning in snowstorms. It's not often that you do, but in a very severe snowstorm, you can see lightning and hear thunder. Okay? Mainly the difference is that you just don't have cloud tops that high in a snowstorm. Snowstorm clouds are usually much lower clouds, and you need a tremendous vertical push. And that's usually only something you're going to find in the summertime, when you've got a lot of heat on the ground, a lot of cool air aloft that warm air runs into, and then it just kind of explodes upward. Wintertime minimizes that. Okay? Yes?
Before you leave lightning,
Yeah.
how safe is it being inside of your metal automobile?
Oh, inside your automobile is wonderful. Why? Because inside those metal wonderful automobiles, you have those tires made out of rubber. And even if they're steel belted radials, the automobile is the safest place to be in a lightning storm. Very definitely a safe place to be. Do not leave your car for a lightning storm unless you run into one of these problems, which is, of course, the flash flood. Then you've got to make a choice. Any other lightning questions? Yeah. Okay.
Sailboats.
Good. Sailboats. I have asked that question to several sailors. They deem them safe because of the body makeup. Although I don't know that I'd want to be around the spinnaker or any of those wet cloth items when it did strike. most often sailors will take their masts down, and if there's lightning and thunder nearby, they'll usually go to a port, safe port. They are generally grounded. Okay, well that might answer part of it then. They seem to, they will. Okay. To answer that question, yeah.
I've seen a sailboat with a metal mast that was hit by lightning.
Yeah.
The lightning came down the mast, went through the hull, and left about 10,000 holes. Through the holes, each about 1/8 of an inch in diameter. It was like a sieve.
Did you take pictures of it?
But the people were not injured. There were people on the boat, and I guess they were shook up a bit, but they were not injured.
Is that right?
Did they get to port? Did they
Wow.
sailed home?
Now this is
Pardon?
They sailed home?
I don't know how they got them.
this is in the bottom as well as the top.
Pardon? The hull was perforated.
Holy mackerel!
Where it came down and went to the water through the hull.
Holy mackerel!
The
Huh?
boat went right off. They couldn't do anything with it.
Is that right? That's pretty awesome. Yeah.
I'm from downstate, towards Binghamton Way, and last October, it was in the middle of the month, we had a severe thunderstorm, which was odd that time of year, but it wasn't a single strike of lightning and then a few minutes another one. It was continuous lightning, and that was scary, and a lot of wind. I've never seen anything like that before. I'm usually the one that goes out and watches these. I love thunder and lightning.
Yeah.
I'm weird that way. It was scary. I went inside. It was just one strike right after the other, all over the place. It must have been
Okay. The general idea is just like this. If I put my hand here and just like that, if you get a very strong updraft and downdraft situation going, you've got your setup, okay, for the production of the electron stripping, so to speak. Again, if the storm is not moving very far, very fast, you can just get multiple charges. As a matter of fact, one lightning stroke that you see is usually not just a single stroke. It's a multiple of maybe 5, 10, 15 individual strokes.
All over. I could see the horizon. It was just over here, here,
Yeah.
here, and here. And that time of year is unusual. I mean, the leaves were changing.
Yes.
They're almost off the trees.
Yeah, that is very unusual. Just had a lot of energy.
Just a clear,
Just a tremendous amount of energy. What I suspect is that the storm had an unusually dry core. Now, why that? Is that when you have a dry core and precipitation's falling through it, you enhance your chances of evaporative cooling, and then you make a very cold, dense core which sinks very rapidly, and at the same time is fed on the opposite side by warm, moist air rising, and there's your dynamo right there. Okay, so I would suspect that. Normally it doesn't happen here in New York State or in the East Coast, but it does happen that way out in, say, Kansas, Nebraska.
That's when the Canadian air and the Gulf air.
Right, then you get that warm, dry air out in the deserts. You have to have that warm, dry air too. It's like a triple component there. And oh yeah, and then of course then that makes for the next stage, which is also 20 minutes. Okay. Yeah. By the way, lightning can come in varieties. The ball lightning. I don't know whether you've ever heard of ball lightning, but this is the kind of lightning that chases people around the house.
Oh, yeah, I've heard about it.
It's some kind of a plasma. It's not really fully scientifically explained, although we do know it occurs and it burns things as it goes through. And people have whacked at things like that with brooms and mist and stuff, or scorched the broom. Very often you've had reports of this thing bouncing around the house. People think it's a UFO. It hits a television and it goes boom, boom. So I don't know what ball lightning is. I've never seen it, but I don't really want to. Okay. The next,
What's heat lightning?
Right, heat lightning is it's a storm that's just far away, and you're just seeing the lightning. It's usually a thunderstorm that's over the horizon. There's no real such thing as heat lightning, okay? It's produced by a storm that's beyond your horizon, and you see the reflection. All right, that's what it is. But it's a storm. It's a lightning storm.
In the Midwest, we used to see it in the summertime when we were dry and you would never get any rain out of it.
Yeah. It's just that the storm is too far away and maybe not working its way in your direction, maybe going, by you in some direction.
It seemed like we never heard the thunder that went with it either.
Well, remember that lightning is instantaneous. It travels at the speed of light, and thunder is really compression in the air. And not only is it slower, but if the storm is 30 miles away, it just may not have any compression by the time it gets to you. Okay, it's like clapping your hands in a room, and maybe out there somebody won't hear you. But if I had a flashlight, you'd all see it. So that's what very often happens. But hate lightning is kind of a misnomer. It's not really something different. It's a thunderstorm that's too far away. Yeah.
What's sheet lightning and how's it caused?
Okay, sheet lightning, it's another variation. Sheet lightning is very commonly in the form of a cloud-to-cloud lightning, okay? And what it is it's not a sheet of lightning itself, but what it is a reflective kind of thing, where there's a cloud behind, and this lightning is going from one side of the cloud to another. It looks like a sheet, but it's really not a sheet itself, because lightning more often than not takes the form of a kind of a cylindrical channel. Okay? Questions? Lightning is neat stuff.
Well, the distance away, sound travels slowly.
Okay,
slower than light.
if you see the lightning and you count to 5 seconds, and hear the thunder, it's a mile. A fifth of a mile per second. In other words, the difference between the light and the sound. Each second is about a fifth of a mile, because the sound is so much slower than the light. Okay? So in other words, if you're counting to 3 seconds, the storm is 3/5 of a mile from you. And if the interval between the lightning and the thunder gets smaller, that storm is approaching you. And of course, it's getting almost going away. Yes?
A number of years ago, my husband was on an aluminum ladder painting, fortunately on the bottom step. And he was across the road, way down, so I couldn't hear him or anything, but I was up at the house, and all of a sudden, he didn't hear anything. But there was the funniest thing, and I looked out at him, and he was on the ground, and he couldn't talk for about 5 minutes. And something, we didn't know what it was. Would that be lightning?
I don't know that I'd want to say, but since your body's nervous system works on an electrical system as well, it's possible that the lightning was close enough to maybe have shorted the system out a little bit.
Well, neither of us heard anything. But I mean, he was far enough away, so I mean, so, you know, that I couldn't hear anything else, but it affected him too. I mean, he was at least 100 yards away from me.
Strange.
Very peculiar.
Very strange. There have been examples of children, blind children since birth, getting a near hit by lightning, and all of a sudden, boom, they have their eyes back. And hearing and things like that. It's kind of a tricky thing, lightning. It's an amazing, it's an awesome power. Awesome power. But I'm not saying yes or no. It's hard to say. I can't answer you.
It was cloudy.
Yeah.
But I don't remember that there was any other manifestation of any kind.
It's possible. It's entirely possible. Okay. Yeah, and of course the old adage of lightning never striking twice in the same place, I think you can put that one to bed. Well, Empire State Building gets hit 20, 30, 40 times in a single storm sometimes. George Washington Bridge in New York gets hit hundreds of times during the course of a few seasons. Lightning does strike you twice. And, just because one tree, was hit once a long time ago, it doesn't mean to run up to it and sit next to it because lightning will strike it. Don't do that. Okay, next big problem we have around here, because of our narrow channels, river valleys, is of course the flash flood potential. Vermont has it probably to a greater extent than we do, because they tend to be a little bit narrow in their river basins than we do. But flash floods are very, very common throughout much of the Northeast. There's a flood warning right now for Long Island, Suffolk, Nassau counties, because they are going to get anywhere from 3 to 8 inches of rain between now and midnight tonight. And they've already had a lot of rain. Okay? They have a low-pressure system that's been sitting there all week, kind of raining down on them little bits and pieces until they picked up probably 8, 9, 10 inches of rain this week. And now this storm is going to move right over the top of them and squeeze out maybe 6 or 7 more inches over the top of them tonight. So they got some problems down there. Flash flooding, though, occurs as a very high volume of water falls over usually a small area, and of course cloaks streams, floods, roads and whatnot. And very often it's formed by thunderstorms which continually redevelop in the same spot. So it looks like the thunderstorm is just staying there. Okay? We call it a train echo in terms of the meteorological sense. Because what happens is the thunderstorm moves, that's producing these heavy downpours, but it dies out and then redevelops back where it started again. And you may have this going on for several hours. They did over in Stowe, Vermont this past June, and they got anywhere from 4 to 8 inches of rain. In some areas got 15 inches of rain in the span of a day. And of course, that produced millions of dollars worth of damage. And if you've been over Stowe in the last couple of months, you can see the damage all over the roadways. It's just incredible. But flash floods are another major cause of concern. People do not react well to these kinds of phenomena. They more often than not take campers, because campers love streams. They love to get their tents right out in the stream, so the next step out is in the water. And unfortunately, with a thunderstorm producing heavy precipitation in the mountains, these people may not even see the storm itself. Okay? It may be raining cats and dogs 20 miles away, and that river may run right past the campsite, and within maybe 15 minutes, the volume of water can rise from, bank full to maybe 3 or 4 feet above bank full, maybe even greater amounts than that. I just came up through Big Thompson Canyon out in Colorado, near Estes Park out there, and they say the wall of water that went past there in 1982 was something like 60 feet high, because there's nowhere for it to go. I mean, there are canyon walls, solid granite walls, and of course, the Big Thompson Canyon is one of the greatest disasters, flash flood disasters this country's ever seen. Destroyed a lot of stuff out there. But in Vermont, this was a very common situation. People take chances with trying to drive across roadways, and that's where a lot of people meet their demise. If you are in a situation where you see the potential for flooding, the road is covered with water, don't drive over the water. Because very often what will happen is a river nearby will have flooded, come over the river bank, come over the bank itself, flood the road, and whatever culvert pipes are running under the road, in case of high water, very often get washed out. And so the next vehicle that runs over that area is running over basically a cavity. So the car goes down into the hole and boom. We've had that around here in Westport. Some very prominent people were killed in a flash flood related event. They drove over a road that was undermined by a river and were killed. Okay? All right. Again, flash floods occur, they are more localized than a general flood. So if you're a flash flood watch or a flash flood warning, it means that if you live near a small stream, there's the potential for that stream to rise very, very rapidly. Okay? And it's different from a flood watch, which is generally a large scale thing. In other words, too much water over a large geographic area. Okay? Okay, next thing that I'll try to move on a little faster here, that you get from large summertime storms is hail. And this is just a very generic picture of a hail storm. This is, of course, hail on the roadways. Hail is very frightening. It can be the size of softballs, even the size of pineapples. Hail we don't usually think of as being a deadly force, but in India it killed recently over 100 people, made 10,000 people homeless because it destroyed everything that's packed. Localized event, but hail that was baseball size or better, hitting the earth at speeds approximating 110 miles per hour. That will put a dent in your forehead very quickly. Kill cattle, strip cornfields, and the like. Very common out west, used car lots. If you ever go buy a car out in the Midwest, kind of just take a look at it from the side and look at the roof. And anytime you see these little ping marks, the probability is the car's been driven through a hailstorm. and they're just about unfixable from that point on. Just drive them that way. But hail is produced by the fact that some of these thunderstorms are so high that their tops go far below the freezing point. Okay? And the circulation patterns of warm and cold currents keep these cloud droplets, rain droplets, and then frozen rain droplets in one of these cycles. And they'll freeze, they'll go down to the lower part of the cloud, which is above freezing, pick up more cloud particles, and then go up and freeze again, and then come down and pick up more cloud particles and freeze again. And this may go on, 20, 30, 40 times until you've got a coating of ice the size of a softball. You take a hailstone apart and cut it in half, you can see the concentric rings of freezing thaw. All those episodes are within that hailstone. Okay? And these hailstones, again, can be a very, very devastating force. And when there is hail, when you do have hail, you know that the storm is approaching a severe level. National Weather Service designates a severe storm as one that has approaching golf ball size hail. Okay? Once you have hail falling out of a storm, the size that you see in this picture, you're talking about severe weather. And the reason for that is there's so much potential now because you've got this freezing thawing episode that you have one of nature's wildest furies. And that starts, of course, with the winds. Okay? This shot was taken in the Midwest. Of course, we have a nice little scope of light in there. But the most significant part of this is this area of clouds right here. We call this a gust front. Because by this time, the air with the ice in it has gotten so cold that it's literally blasting downwards at maybe 50, 60, 70 miles per hour and falling to the ground and then spreading out. A little bit like if you took a hairdryer and some powder on the ground and you pointed that hairdryer straight down. Okay? It hits the ground and it spreads out in all directions. Now, this kind of stuff very often is confused with tornadoes. They're very closely related, although this is nowhere near as severe as a tornado itself. But it's the start of the potential for tornadoes. This gust front very often is called a squall line, and it's usually a bank of winds that all of a sudden hits at 40, 50, 60 miles per hour. We had one here this past summer, and I really strongly believe that what went through in June of this year was a gust front, not a tornado, although there may have been a tornado above the ground. What did the damage in Saranac, what did the damage over near Mark's Sawmill and places like that, I believe, was one of these. It's a gust front. And the way the descriptions have come to me, I really think that we're in the ballpark with one of these. It's a core of very cold air plunging down to the surface and then scattering in all directions. And what this does is it produces damage that, well, you can almost visualize it as it occurs. Okay, here's another gust front as it's starting to whip in. Dust and everything goes flying out in very, very defined direction. Okay? Now, we call these things downburst. In aeronautical terms, they're either a microburst or a macroburst. It depends on the size. Okay? You've all heard of the major disaster in Dallas a few years ago, that plane that just quite didn't land. It was hit by a burst of cold, dense air. This is one of the dangers that this kind of situation produces. Macro and micro bursts can take a plane at 30,000 feet or 20,000 feet and drop it 3,000 or 4,000 feet in a few moments. Okay? And it's really interesting. I was talking to a stewardess about 3 weeks ago who was in a plane that dropped something like 1,000 feet. She says, everything just comes right out of the seat. I mean, people float. I mean, drinks float. Water floats. It's just like being in one of those special aircraft that they train the air.
Wind shear, is that another name?
Yeah, wind shear is very often associated with this. wind shear is usually a twisting. In other words, you got a surface wind from the south, and you go up 1,000 feet, and it's from the east. That's a vertical wind shear. Okay, and there are other horizontal wind shears as well. But this would be a shear in a sense, but a very specialized one because it's a downburst. Okay, and again, their diameters usually tell what's going on. Here's an example of that blow dryer effect. Here we have a column of air that's moving down, and I think you can see, although probably not very well, the development here. Okay, you see how that's curling over, just like if you aim a hairdryer down into a pile of dust. Okay. Now, we're talking about the difference between the damage that's produced by a tornado and the damage that's produced by one of these micro or macro bursts. Everybody, of course, when they have a damaging wind, everybody thinks it's a tornado. And so what National Weather Service will do is they'll send out trained spotters that will look at the debris field, okay? And in this case, you can see that debris is in all directions, twisted around, okay? This is very, very definitely a tornado track. You've got a high amount of damage in the middle, everything's kind of twisted around. This is a line type of wind, okay? This is that downburst that scatters out, okay, in a micro or macro burst, hits the ground and goes this way. This was a trailer at one point, and it's been sheared out in this direction. So when we go in and we look at to see whether there was a tornado or not, this is some of the stuff that really plays the part. You know, people may report funnel clouds and they can see all kinds of stuff, but if the damage fits that pattern on the right, it probably wasn't a tornado. Okay, it probably was a microburst. Okay, a line wind. Okay. Let's see. I got some tornadoes here. Here's a neat tornado. Here's a skinny one. Okay, now tornadoes themselves very rare in this area. We've had them. We probably had some tornadoes in the air that didn't touch down back in June. We did have a tornado back in 1980 that went across Port Kent. And maybe some of you remember that. It knocked out a lot of trees. There's still a path there. You can still see it going up that second hill down toward Keysville. It flipped some trees over down to the ferry dock. It did some damage. It didn't kill anybody or anything. But this is a full-class tornado. Now, what happens to make a tornado still is a little bit uncertain. What we have is very, very strong air moving downward, very strong column of air moving upward, getting this rolling effect. Okay? And then because of shearing in the upper air, this rolling cloud then starts to tilt. As it starts to tilt, its base, close to the bottom, starts to become narrow. I'll show you another picture of one, and then there's another one. This is a classic funnel cloud. Okay, here it's very wide, here it's very narrow. But you got to remember that this whole thing is in motion. Now let me show you a little bit of what that is like. And I need a volunteer here, and I need some lights. Okay, we're going to put you in a tornado. We're going to do it back here. How's that? Okay, this is a little bit of how a tornado works. What time is it, Rick?
8:05.
Okay, this is supposed to go at 8 o'clock, right?
No, right on.
Okay. Would you sit down there for me? Now, I want you to just kind of sit Indian style. Can you sit Indian style just like that with your legs crossed? Very good. And what I'm going to do is I'm going to spin you around. You feel that? Okay, you like that? All right? Now, here's what I'm going to ask you to do. These bricks are weights, okay? And I want you to hold one in one hand and one in the other. Okay? Now, you realize they have powerful holes in them, right? So you can hold on to them, right? Okay. Now, what we're going to do is we're going to put our arms as far out as we can, okay? And you put them way out there. When I say free, I want you to bring them in right into your lap like that. Don't do what my kids at school do. You know what they do at school? They take those bricks like this, they go, no, I'm not kidding. say now, bring him right in. Ready? Bring him in. Woo! Now bring him out. Ooh, bring him in fast. And bring him out. Ah, okay. Now what's happening? Bring him in. Can you imagine if I asked you to stand? Okay, how's that? I don't want you to get sick, so. Okay. Now, you've been inside a tornado. Okay, what little physics thing, which we call the law of conservation momentum. What happens is, just like the ice skater, when that ice skater starts pulling her arm, she spins around faster. Well, what happens is this great big cloud, which is turning and turning and turning like this, starts to get tilted. Friction narrows it down at the base. It's got to conserve that momentum. So as it narrows, its wind speed picks up. So that in a tornado like this, and this is a middle-sized tornado, perhaps having winds of in excess of 100, 115, 20 miles an hour, you get this very, very narrow, very rapidly spinning column of air right here. Okay, and this is what does most of the damage. Now, in a tornado, even though this is the center of low pressure, houses don't explode. You probably heard the old tale that before a tornado, what do you have to do? You got to run around, you got to open up all your windows, or something to that. I was taught that when I was in college. I won't say how many years ago, but the first thing you want to do is you got to open up all the windows, equalize the pressure inside and outside during a tornado, right? Wrong. Okay? What does the damage is the tornado winds themselves and producing what we call a Bernoulli effect, which is the same effect as what keeps an airplane flying. Air rushing fastest over the top of the roof of a house, because it all kind of gets gathered there and then it kind of squeezes over the roof of the house. What that does is create a little area of low pressure and lifts the roof up, just like it lifts the airplane wing up. So the roof comes off, and then the walls come tumbling down. So it kind of gives you a neat effect. It's the same reason why when you turn the shower on, you're standing in the shower and the shower curtain's always there. It doesn't blow out of the tub, it blows in. That's because that column of air is moving very fast on the inside of the tub, and it moves in to you. Okay? Same reason why curveball works. Okay? Curveball is a spinning ball, right? When you're spinning a curveball, it's going like this. On this side of the ball, where that ball is turning, it's making the air go faster. And that's creating low pressure. So as that spin goes this way, low pressure here, high pressure over there, it wants to make the ball go that way. And that's why a curveball works. Okay? So now you know, weather and curveballs are all related. So anyway, what happens here is, these can produce winds in excess of 200 miles per hour. Some estimates of the big one, the Wichita Falls in April. This was a granddaddy. This is one heck of a tornado. Probably you all heard about it at least. In 1979, killed many, many people. This is a Category 5, the biggest, the baddest type of tornado you could ever have. And it probably produced winds in excess of 200 and some miles per hour. And what it did is it just kind of obliterated an entire section of Wichita Falls. Just incredible dynamo right there. It lifted great amounts of debris, swirled them around. You can see some parts of houses in there, maybe parts of car rooms or whatever, scattering around. Again, thank goodness, only 2% of all tornadoes ever reach this category. And this is the granddaddy of all. And something like 50% reach the category of this one right here. Whoops. All right, this is most common. This is a rope tornado. Very short-lived. Usually the narrower they are, they don't last very long. Sometimes they'll whip around here for a few moments and then just disappear. And then they'll start up here, disappear. And maybe two of them will form. They'll go, do-si-doing around one another and then disappear again. They're the weirdest things you've ever seen. But again, it's all produced by these very quick-moving columns of air spinning. Whoops. There this is your most common type right here, and this usually has a little bit of enough of a longevity to do some damage. Okay. What's kind of neat about tornadoes, they've done some funny things for us too. Anybody ever hear the expression "raining cats and dogs"?
Yeah.
I don't know whether that ever happened or not, but I do know of reports of it raining frogs and salamanders. And if you went to church in Lexington, Kentucky in April of 1938, you may have come out at noontime to witness a fish fall. Not a fish fry, a fish fall, as fingerlings up to maybe 7 or 8 inches in diameter of length of trout were falling on the church grounds as people walked out of church. Probably this tornado in the distant went up the river, scooped up some things out of the river, and then dissipated, and then of course the things fell to earth some 20, 25 miles away, and of course caused some problems. Some of these things are related to some of the biblical events, the red rains, some of the plagues that were produced by Moses. Some people think that they might have been produced by some weather phenomena. I don't know. I wasn't around at that point, but I don't know. But again, they have produced some kind of interesting things. There's supposedly a well-documented story of a gal or a guy and a horse being carried off by a tornado and falling to the ground some hundreds of feet where they left. And the horse landed in a tree, and the guy landed on the ground and broke his arm. I think the horse died. I don't know that I believe that one, but there have also been stories of people having their entire homes obliterated above them while they were in the basement, and they sort of looked up into the center of the tornado, looking at nothing but clear skies. I don't know about that one either, but what damage is produced? What damage is produced by a tornado is mostly shrapnel. Straw drives into brick, just like bullets firing into a wall. They travel right into a brick surface. Roofing shingles just behave like shrapnel from bombs. They just cut right through you. Several arms and legs and all kinds of stuff. Little pieces of plastic roofing tile traveling at 200 miles an hour, just like a machete. And so those are the things that really cause the problem in the tornado. Okay. Are there any questions? We can turn our light on here. I'm going to give this a rest because this is an old projector.
Is the circulation about the tornado always in the same direction?
Counterclockwise and inward.
Counterclockwise.
Yes.
And in the
southern hemisphere.
Southern hemisphere would be opposite, right?
Yes.
Okay.
Yeah.
Just like a hurricane then, huh?
Exactly. But of course, hurricanes are the most, in terms of total energy, the most massive storms on Earth. Tornadoes are just little whimpers compared to hurricanes. Hurricanes have speeds in excess of 200 miles per hour, as Hurricane Gilbert displayed as it crossed the Yucatan Peninsula. And they produce so much rainfall. Most, by the way, deaths in hurricanes are not produced by wind, they're produced by flood. The Galveston tornado back in 1906 killed something like 6,000 people, and most of them were killed because of the sea surge. Hurricanes tend to push a great volume of water towards land with this counterclockwise circulation. So in other words, they bulge the sea up in one section of the storm, and when it makes landfall, it produces the storm surge. The storm that hit Charleston, South Carolina 2 years ago was indicative of that.
What's the difference between like this and a cyclone?
Cyclones and hurricanes and typhoons are really all the same type of storm. In Australia, they call them willy willies. And there are other names for them, but they're all cyclonic types of storm. And they all have patterns that move in the same direction. Just that hurricanes are Atlantic, typhoons are generally Indian Ocean, Eastern Pacific, and cyclones are Indian Ocean phenomena, and typhoons are Pacific Ocean.
Well, I came from the Midwest, and we used to have what we call cyclones, and I don't remember that they ever were circular. It seemed like it was more like a tremendous wind.
Oh, okay. A cyclone sometimes is a tornado, depending on where you live. They often confuse cyclones with water spouts too. If a tornado goes over a lake or an ocean, it causes a water
Well,
spout.
there's no water near. This is
I don't know.
happening.
I'm not sure I can answer your question.
Because I looked it up in the dictionary as far as the two were concerned, and the definitions were almost exactly alike
For the
for the cyclone and the tornado.
tornado, yeah, it could very well be that that's what they're called. Even
But we
that.
just never, I mean, when we did have we had a real tornado go through down the southern part of the state. It just made a swath right through.
Mhm.
But that was really called a tornado,
Yeah. different
from the cyclones.
Okay, again, a cyclone, in terms of the definition, is a hurricane type, tropical type of storm. It's a low pressure center without fronts. It's a heat machine. And they're more common, they're always ocean storms. They always begin with the ocean and they usually die out over the land. So it could be that it was a remnant of a hurricane or something like that. I'm not sure.
Well, I come from the Midwest too, and we used to have cyclones regularly, what they called them. And they were, there wasn't much lift to them. They were a driving force horizontally.
Yeah, that's what we
Took out down trees and took the barn roofs off, and
Sounds like a straight line wind produced by a downburst.
but they were always did a lot of damage.
Oh yeah, I'm sure. I'm not saying they can't do damage, right? Though straight line winds do damage. Just ask the people up in Saranac. Did some damage up there, but I think that was a straight line wind, a downburst, and then in all directions.
In that regard to that one in Saranac, my son lives up on the, above where the storm was. In other words, he's up on Chazy Lake Road.
Oh yeah.
They could feel that storm going, or hear it going through below them.
Yeah.
It actually went down the valley below them.
Okay.
And they could hear it.
Yeah. Okay. Yeah. I think that's what it was. A straight line wind. It's a gust front. Yeah. That's right. That's right. That's very common to see in those types of storms. Any other questions? Storm-wise, anything? Anybody got any old good stories about storms here?
I have a question for you.
Yeah. Go ahead.
We have a lake situation this year.
I'm sorry?
We have a lake situation this year where the level is at least a foot, maybe a foot and a half higher than it was last year. Is that going to have any effect, or you know, on what the lake level will be this winter and next spring? I've had that question asked of me. I'm asking you.
Well, I'll tell you, it's a foot higher now than it was a month ago.
Yes, it is. I know. My dock went underwater.
Whether that has any, of course, you're looking at it in the sense of what has already happened. I don't think it's telling us what's going to happen in the wintertime. But of course, if we start out with a very full lake in the end of summer, as the temperature decreases, evaporation decreases, and the amount of water that is basically taken from us gets smaller and smaller. We call it potential evapotranspiration. So as we get into the winter months with a high lake, when we start to build up snowfall and whatnot, if that lake does not go down, it could tell us something about next spring.
The Lake Champlain Transportation is very concerned with lake levels because of the rafts on their lakes.
Yes.
They have kept records of the lake levels for about the past 30 years. And of course, there's a tremendous amount of variation, especially in the spring and summer. But what I find interesting is that irrespective of what happened in the spring and summer, when you get into the fall, like November and December, the curves all came together. So the answer to your question was the lake will return to what maybe historically it's November and December levels. Instead of back as high up.
If our precipitation pattern changes.
Well, it's controlled by the rock ledge at St. John's, of course. And it's like a weir. And of course that controls the lake level in addition to evaporation.
Yeah, that's it.
But my just answering your question is that according to their curves, irrespective of what happened to the lake in the earlier part of the year, like in the late spring and summer,
Right.
it always seemed to become more or less uniform in November and December.
That's interesting.
Well, isn't that controlled by the rivers that flow out into the ocean?
I know
I
we've
don't
been,
answer your question. Your duck's going to come out of the water in December.
That would make it cool.
yeah, I know the lake has been up over 101 feet. I would expect that if we had a lot of rain and the temperatures went down, we'd have some problems with that lake, especially with the development that's been going on around it.
Another interesting comment, there's a, what they call Smith's History of Vermont, published in 1794. This little fellow is running all around the country measuring temperatures of wells and the air temperatures and lake levels. And the lake levels in 1794 and the variation are not too different they are today.
That's interesting.
That's 200 years ago.
We built a house, a new house, within 20 feet of the Lake Champlain, back in 1976. We had spent 6 weeks out of the country. And when we came back, all of our friends gave us pictures of our property. It was covered with water. Covered with water. That's the year it went up to 101.9.
Okay, yeah, that's when they had
So we built the house anyway and just put an extra layer of blocks on the foundation. It hasn't come back since, but it can anytime. Right?
Yeah, historically speaking, there are what we call the 50-year floods, the 100-year floods, perhaps 200-year, 500-year, 1,000-year floods. And again, they're controlled basically by changes in, short-term anyway, climatic patterns. And we can we can almost say that sometime in the near future, Lake Champlain will occupy most of Route 9 North, where those condos are, as well as probably choke out the roads on Cumberland Head and do some major damage in other places. We can't say when that's going to happen, but historically the lake has been that high and probably has gone down to maybe 85 or 90 feet on the other side of the pendulum. So again, because of these fluctuations in climatic patterns, these short-term patterns that we go through, I think it's impossible to say that we're going to have a flood next spring, but there's a chance. There's always a chance when you live near a body of water that it's going to come up. And especially in the wintertime, if ice chokes the outflow ports, and then things go up from there, it's possible we could see a major problem if the lake is high in the spring. Okay. How you guys doing?
And finally get a building seawall.
Anything else? Yes.
What's the potential for good snowfall this winter?
That's the third time today that I've been asked that question. It's impossible to say. I wouldn't lie to you. We can't tell right now. We are on the verge. We've gone through a period of several very dry years. We are right now about 4.5 inches, depending on where you are, above normal, and we're already above, for this month, at least 1 inch. Again, some areas are 3 or 4 inches above normal this month alone. Because of that, and being in a kind of wetter position, I would say that probably this year we're looking for a snowier winter than the last several. Okay? So for those of you that are looking for snow days, okay. Yeah.
I don't know if this is the right time to ask this question, but when did Mount St. Helens explode?
1980, May 18th.
All right. The reason I'm asking is, several months after that exploded, I was flying east out of San Francisco, and the man sitting next to me was an environmental scientist flying back east, and he had been to a conference, and he was wringing his hands in glee. This is the first time we've had an opportunity of studying the effects of a volcanic explosion firsthand. Just great. But what he was saying was that the tremendous amount of ash thrown into the air was floating east across the continent.
Yep.
And leaving the continent around Gander somewhere, going over towards, spiraling around and coming down around the Carolinas, and a big spiral. or at least their prediction, I guess, because of the effect of all this ash in the air, does irrespective of what you consider the normal weather patterns in your locality, they're going to be disrupted, or not just, they'll be different for the next 5 years.
Yeah.
Does that make sense?
Well, they said the same thing about when the space shuttle went up, and comparatively speaking, the space shuttle put about as much pollutant particles as Mount St. Helens when you compare it to a large volcano. Mount St. Helens was a little pipsqueak, and though it looked pretty awesome, Krakatoa back in 1883 broke up a 5-mile cubic island that just blew it to smithereens. Mount St. Helens on a scale of 1 to 100 was maybe at 9/10, and Krakatoa was probably at 50. Tambora in 1815, which produced the year without summer here in 1816, was probably at 78. Now, the first time that Mount St. Helens went up, it was called Mount Maxima, and it was a big one. It was probably 80 on the
That's a
scale.
basic question. Do you feel that is currently affecting our weather patterns?
If it is, I don't know that we can. The problem is, right now, I don't know that we can separate things like La Nina or El Nino, depending on the circulation pattern in the Pacific, volcanic activity, human activity, and natural climatic change, things like sunspots and whatnot. There are so many things going on that we just can't, we don't, right now anyway, we just don't know which is having the greatest amount of impact. You know, the first things that came up when this greenhouse effect started to be very overplayed, and I'm not saying it's overplayed, but it has been overplayed in my sense, in my feelings, looking at the temperature changes that are predicted by the year 2050. They're saying we're going to have, by the year 2050, a climate very similar to Jacksonville, Florida. Okay? One of the little blemishes that researchers have fallen into, or the problems they've fallen into, is that when we look at these long-term, 200, 300-year-old patterns, looking at temperatures, how are those temperatures done? Well, first of all, land temperatures, thermometers in those days were not standardized. Where we take temperatures now, standard meteorology station, standard weather station, 6 feet above the ground, in a little box, out of the sun. It wasn't done that way 100 years ago. Consider the fact that 70% of the entire Earth, now we're talking about greenhouse effect affecting the entire Earth, not just land. 70% of that's water. How much data, hard weather data we have coming out of the oceans? Not very much. And yet the oceans may be the biggest absorber of solar energy. Probably is. Okay? When these researchers did that first analysis, they looked at the ocean, the shipping records, okay, of these boats that were coming across 1700, 1800, 1900, okay? And they used to do a certain thing with those little thermometers that they had. They used to hook them at a certain point on these ships, okay? But of course, as time went on, the ships got bigger and bigger and bigger, and those thermometers got higher and higher and higher above the surface of the ocean. So you're seeing an anomaly. If you take the temperature near the ocean surface as opposed to the temperature 15 feet to the bow level, you're going to get a totally different reading.
There's one thing more finite, and that's snow levels, total accumulated snow.
Pardon?
And snow depth is a more finite measurement.
In what sense? I mean, over a
Well, typically the meteorological office at McGill University was first established about 1850.
Mm-hmm.
And then around 1950, they published the results of it was called 100 Years of Weather at Montreal.
Mm-hmm.
And they gave all the usual things like temperature and so on. And they did quote a warming up figure. But the significant thing was that the snow depth in Montreal currently is averaging only 1/2 of what it was 100 years ago. Now you can measure, I mean, foot rules and foot rules. You know.
Sure. But again, we cannot necessarily separate that from the other things that are going on. It's not saying that Montreal isn't having a small amount of snowfall, but look upstream and look downstream. Are they not having more? And that's seemingly what we're seeing. There's a lot of variation. And the complexities, the latest that I've seen shows that the greenhouse effect will have a warming. I think it was just, I think a Scientific American, one of the latest articles, where they tried to correct all of these ocean anomalies and land anomalies, and they made a pretty strong attempt at doing that over 10 years. They forecast now the greenhouse effect might cause a 1/2 to 3/4 degree change over the next 50 years.
That can be a lot, can't it?
That's significant. Oh, definitely significant. But it's not the 5-degree change.
Other factors like, we have photographs of my grandmother sledding or on snow off the Riverville barn. Well, that was down in Maryland. And the snow is drifted, God knows,
That's
10
right.
feet high. And they haven't had 10 centimeters of snow in the last 15 years.
That's right. That's right. There is no question about the hard winters in the past. They're well documented. But again, we cannot separate that from normal climatic change. We just cannot do it. Yes, the winters back then were hard. We're in a warming cycle right now. We've had some cooler years than normal in there, but there has been a definite tendency of going up. But when you compare it with pollen and you compare it with tree ring data and all that from thousands of years ago, we see this pattern of 100 years, 200 years. And so how the greenhouse effect is masking what we're supposed to be getting now is still really a guess. Of course, we're putting more carbon dioxide in the ocean now than ever before. I mean, in the air, than ever before. There's no question about that. But what it's contributing to our temperature globally is really a guess right now. I wish, the new reports are that termites, I just came from the NCAR, National Center for Atmospheric Research. I was there a week and a half ago. Estimates are that termites put an unbelievable amount of carbon dioxide in the atmosphere that we hadn't even considered before. Okay, it wasn't even in the earlier models. And this is a study that's brand new and will probably be coming up now pretty soon. But termites, because of their completeness of their digestive, they digest food so completely, they convert almost all of it into carbon dioxide. They are tremendous carbon dioxide producers. That hasn't even been considered.
Hope they don't make them a protected species.
Yeah. Let's hope. Yes.
What about the carbon dioxide coming from limestone and acid rain? There's a tremendous storage of carbon dioxide in limestone over the world, and a little bit of acid rain dissolves that, and what does it do? It comes right up into the atmosphere.
True.
And what proportion of the total could that be attributed to?
This is very true. And on the other side of the coin, we don't know just exactly what the effect is of ocean plants utilizing the carbon dioxide and becoming more prolific. We don't know that at all. So the greenhouse effect is very real. I mean, don't misunderstand me. There is a very real greenhouse effect. But how it's being manifest on Earth is still not well understood. And there's going to be a lot coming out about it. And of course, there has been a lot about it in the past 10 years. But it's still a major study. And probably not a lot more than that. We should, though, do what we can do to save trees, recycle, reuse, and use less of what we're doing. I mean, I think that's just jurisprudence. We as a species are changing this earth at such a phenomenal rate that eventually one of these drastic changes will be our demise, I'm sure. Whether it's the greenhouse effect, the ozone problem, or any number of things that could be around, that we don't even know about. But we should recycle, use less of what we use, and return what we can to the environment in the best way that we can. Because we're basically destroying. We have been destroying the earth, and once we put some of it back, there's not enough for our kids. Simple as that. So, maybe I should leave you with that note. significant going on in your area, wherever you are, give us a call. I'd love to talk to you, and love to hear what kind of weather's going on. If I'm not reporting it, I want to know. Okay? And please, I'm serious about it. Yeah.
There have been a couple of interesting storms, just local storms, out on Cumberland Head. A couple, 3 weeks ago on a Sunday night, all of a sudden, just without warning, gust of wind took out docks and so forth. Now, it didn't happen in Plattsburgh, it didn't happen even on the tip of the Cumberland Head. Just went through that one place. Then out near the tip of the lagoon place, about a week later, they had a terrific storm, went down the lake, along the shore. But they seem to be very narrow.
Yeah. And these are things that jump in between the radars, and we never see them.
Yeah, but they're violent, but they're very narrow.
Yeah, I know St. Albans got socked with a 60-mile-an-hour wind last year. We didn't know anything about it. Did a lot of damage up there, too. Something happens, give us a call.
Just a couple of announcements before you leave, ladies and gentlemen, please.
Fantastic.
Can I have your attention, please? Just a couple of announcements. Please take a couple of minutes and complete the evaluation form. Not only does it give you a chance to evaluate this evening's presentation, but it also gives you a chance to give us some input for future programs, because we do use this to put together our summer program series each year. This evening concludes our 1990 summer guest presentation schedule in its entirety. We thank you all for coming to some of the programs that we've offered. We are going to be offering some programs, not on a weekly basis, but they'll be occurring every once in a while throughout the year. And the next one that we have coming up, it won't be taking place here, but it's scheduled for Friday evening, September 7th at 7 o'clock at Cumberland Bay State Park in the Recreation Room. And this will be a New York State certified waterfowl identification course. And Ed Gardapi will be the guest instructor, the guest speaker. And that, as I said, will be at the Cumberland Bay State Park Recreation Room, which is located on the western end of the bathhouse at Cumberland Bay. At this time, I'd like to ask Gib to come forward. And on behalf of the Thousand Islands State Park Recreation Historic Preservation Region, I'd like to present Gib with this Dixie Adirondack print as a token of our appreciation for this evening's outstanding presentation. Thank you. Once again, thank you all for coming.
Good
See you
season.
again sometime. Take
Good
care.
season.
Have a safe trip home. Thank you.
Thank you.
Thank you for coming down. My volunteer.